Hey there, and welcome to This Explainer. Today, we are unpacking something absolutely, literally fundamental. We're going to uncover the hidden operating system of the physical universe. We'll be looking at the rules that govern everything around us. And just as importantly, we're going to shine a spotlight on the historically overlooked figures, specifically trailblazing women who actually helped write that code. It's a fascinating story of paradigm-shifting science and the societal barriers that brilliant minds had to overcome just to do their work. So, let's get started.
Okay, let's dive into this. It's really easy to think of physics as just abstract formulas on a dusty chalkboard, right? Something totally disconnected from our daily lives. But what actually makes the everyday objects you touch, use, and rely on actually function? To ground this abstract concept, let's look at something you probably have within arm's reach right this very second, your smartphone.
Because your phone, it is basically a masterpiece of applied physics. When you inevitably drop it, we all do, mechanics are at play in that shatter-resistant glass. Thermodynamics ensure heat dissipation, which is exactly why your battery doesn't just catch fire in your hand. The battery current and the radio waves connecting you to Wi-Fi, that's all electromagnetism. Every single photo you take and every tiny pixel lighting up your LED screen relies on optics. And the microscopic transistors inside the microchip, well, that relies entirely on quantum mechanics. In fact, to put that into perspective, those transistors are now engineered to be literally smaller than a single biological virus. It's the hidden engine powering that little device in your pocket. So, taking a step back from the smartphone for a second, how do we actually define this massive field? Well, physics is the fundamental science concerned with matter, energy, space, time, and how they all interact with one another. It is the ultimate quest to understand the rulebook of the universe, and I mean the entire universe. From the mechanics of the absolute largest swirling galaxies billions of light years away, all the way down to the strange, vibrating subatomic particles that make up the atoms in your own body. Now, what's really interesting about this slide is how clearly it shows the timeline of physics splitting into two very distinct eras, classical and modern. Classical physics deals with the world exactly as we intuitively experience it, everyday sizes and everyday speeds. But modern physics, which was really born in the 20th century, deals with the absolute extremes. We're talking things that are incredibly fast and things that are incredibly, unimaginably small. Let's look at the classical side first. This is the science of the tangible world. Mechanics explains the forces of motion. It's the reason why your car actually stops when you slam on the brakes, or how a suspension bridge manages to hold up thousands of tons of concrete and steel without collapsing. Thermodynamics is all about heat and temperature. It's the science that allows your refrigerator to keep your food cold. Electromagnetism gives us household electricity and motors. Optics bends light so eyeglasses can correct our vision. And acoustics dictates how sound waves propagate, which is exactly why plucking a guitar string makes music instead of just random noise. But then, we hit the 20th century, and things get weird and wonderful. Modern physics steps in to explain those extremes I mentioned. Albert Einstein's relativity completely changed our understanding of space and time. And it's not just theoretical either. Did you know that the GPS satellites orbiting Earth right now move so fast and are so far away from Earth's gravity that time literally ticks slightly differently for them? If engineers didn't program those satellites with relativity equations to constantly correct their clocks, your phone's GPS would fail in a matter of minutes. No joke. Meanwhile, quantum and nuclear physics unlocked the subatomic world, giving us everything from the semiconductors in our laptops to life-saving PET scans in modern hospitals. Which brings us to Section 1, the fundamental science, building blocks of other disciplines. You see, physics doesn't just exist in a vacuum, because every other natural science borrows from it. You really cannot deeply understand fields like chemistry or biology without it. In chemistry, it's physics that explains atomic orbitals and the electrical forces that cause chemical bonds to form in the first place. In biology and medicine, the transmission of a nerve impulse traveling through your body is fundamentally an electrical process. Our joints act as physical levers, and medical imaging like MRIs and X-rays is just pure applied physics. Engineering uses it for aerodynamics and the fiber optic cables that literally power the entire global internet. Even earth science relies heavily on thermodynamics to understand global climate and complex ocean currents. Physics is the bedrock of the whole shebang. Let's move to and see how this builds across human history. The evolution of physics is really the evolution of human thought itself. Back in the ancient world, thinkers like Aristotle relied mostly on observation and logic. But in the 16th and 17th centuries, the scientific revolution changed everything. Folks like Galileo and Newton introduced the scientific method.
demanding empirical evidence and rigorous math. Fast forward to the 19th century, and James Clerk Maxwell brilliantly unifies electricity, magnetism, and light into one package. And then boom, the 20th century delivers massive paradigm shifts, with relativity and quantum mechanics completely upending our understanding of reality.
However, as we look at this incredible historical arc of discovery, we absolutely have to address a glaring systemic flaw in how this history was actually recorded. For centuries, science was an incredibly exclusive field, and we must recognize the structural barriers that were firmly in place. This brings us to a well-documented phenomenon known as the Matilda effect. This is a recognized historical bias where the groundbreaking discoveries of female scientists were frequently attributed to their male colleagues or even their husbands. Women were out there doing the brilliant, world-changing math and lab work, but their names were actively erased from the textbooks and the awards ceremonies.
Which brings us to this number, 2. This represents the number of Nobel Prizes won by the legendary Marie Curie. She didn't just overcome the barriers of her time, she completely shattered them. She was the first woman to ever win a Nobel Prize, and to this day, she remains the only person, man or woman, to win Nobel Prizes in 2 completely different scientific fields: physics and chemistry. Her pioneering research on radioactivity completely rewrote our understanding of matter. Actually, fun fact, her original lab notebooks are still so radioactive today that they literally have to be kept in lead-lined boxes. And her incredible work paved the way for modern cancer treatments. But unfortunately, not every trailblazer received Marie Curie's level of recognition. Take Lise Meitner, for example, a brilliant physicist who literally co-discovered nuclear fission, the splitting of the atom. It was her theoretical breakthroughs that made the entire discovery possible. Yet, when the time came for recognition, the Nobel Prize was awarded solely to her male collaborator, Otto Hahn. Her undeniable, historic contribution to science was essentially swept right under the rug by the establishment of the time. And the pattern continued. Consider Qin-Sheng Wu, rightfully known as the First Lady of Physics. She conducted the famous Wu experiment, an incredibly complex procedure that experimentally disproved a fundamental concept called the law of conservation of parity. Essentially, she proved that nature actually favors a left or right-handedness at the subatomic level. It was a staggering breakthrough in nuclear physics. But what happened? The male colleagues who had merely proposed the theory received the 1957 Nobel Prize in Physics. Qin-Sheng Wu was entirely omitted from the honor. Despite these massive barriers, women have continually driven the field forward. Let's celebrate a rapid Hall of Fame here, right? Think of Katherine Johnson, the brilliant African-American mathematician and physicist at NASA. Without her manual calculations of orbital mechanics and trajectories, the first U.S. human spaceflight simply wouldn't have been possible. And looking at more recent history, we have absolute titans like Donna Strickland, who won the 2018 Nobel for her groundbreaking advancements in ultra-short laser pulses, and Anne Louvier, who took home the Nobel in 2023 for her incredible work in electron dynamics. So the crucial point is, promoting equity in physics and STEM as a whole isn't just about correcting old history books. It is an active, ongoing effort required today, because while progress has certainly been made, women still remain underrepresented in physics faculties and industries globally. Achieving true equity means actively acknowledging the implicit biases that still linger around us. It means ensuring equal participation in labs and completely dismantling the structural barriers that might discourage a young woman today from pursuing the physical sciences. Physics is the foundational framework for understanding our universe. But science is a human endeavor, and it relies on all of humanity's brightest minds to keep moving forward. So I want to leave you with this thought to ponder today. How will dismantling structural barriers today unlock the physical discoveries of tomorrow? When we ensure that absolutely everyone has an equal opportunity to look through the telescope, run the complex equations, and conduct the experiments, what hidden engines of reality will we discover next? Thank you so much for joining me for this explainer, and hey, keep questioning the universe around you.